Welcome to Shri Learning Academy. Let's simplify mutex versus semaphore. Have you ever noticed that sometimes in operating systems, two tools look almost identical at first glance, but behave very differently when you actually use them? Mutex and semaphore are exactly like that. On paper, both are used to control access to shared resources and prevent race conditions. But once you start working with them, the differences become very important, especially in real-world system design. A mutex, short for mutual exclusion, is the simplest form of control. Think of it like a key to a room. Only one person can hold the key at a time. If someone has the key, no one else can enter the room. Once they are done, they return the key and someone else can use it. In operating systems, a mutex works the same way. Only one thread or process can lock the mutex and enter the critical section. Others have to wait until it is unlocked. Now let's take a simple example. Suppose two threads are updating the same bank account balance. If both try to update it at the same time, the result could be incorrect. With a mutex, one thread locks the resource, updates the balance, and then unlocks it. Only after that can the second thread proceed. This ensures correctness. The key idea here is ownership. The thread that locks the mutex is the one that must unlock it. No one else can do that. Now let's shift to semaphores. A semaphore is more flexible. Instead of a single key, imagine a box containing multiple tokens. Each token allows one person to access the resource. If there are three tokens, then three people can use the resource at the same time. Once all tokens are taken, others must wait. When someone finishes, they return a token allowing someone else to proceed. Semaphores come in two main types, binary and counting. A binary semaphore behaves somewhat like a mutex, allowing only one access at a time. But the important difference is that semaphores do not enforce ownership. Any thread can signal or release a semaphore, not necessarily the one that acquired it. This may sound like a small detail, but it changes how they are used in practice. Let's take an example where semaphores shine. Imagine a parking lot with 5 parking spaces. Cars enter and leave continuously. You can use a counting semaphore initialized to 5. Every time a car enters, it decreases the count. When a car leaves, it increases the count. If the count becomes 0, new cars must wait. This is something a mutex cannot handle because mutex is strictly one at a time, while semaphore allows multiple simultaneous accesses. Another important difference comes in terms of usage intent. Mutex is mainly used for protecting critical sections, where only one thread should execute a piece of code at a time. Semaphore, on the other hand, is often used for signaling and coordination between threads. For example, one thread can signal another that some work is completed. This kind of communication is not the primary role of mutex. Let's make this even clearer with a practical scenario. Suppose we have a producer and a consumer. The producer generates data and the consumer processes it. You can use a semaphore to signal that data is available. The producer increases the semaphore when data is ready, and the consumer decreases it when consuming. Here, the semaphore is acting like a communication tool. A mutex alone cannot handle this coordination efficiently. There is also a difference in behavior when things go wrong. Since mutex enforces ownership, it prevents accidental unlocking by the wrong thread. This makes it safer for protecting shared data. Semaphores, being more flexible, can lead to bugs if not used carefully. For example, if a semaphore is released too many times, it can allow more access than intended. This requires careful design. Another subtle but important point is priority inversion, which we briefly touched earlier in synchronization issues. Both mutex and semaphore can face this problem, but mutex often comes with mechanisms like priority inheritance to handle it better. This makes mutex more suitable in systems where strict control and fairness are important. If we step back and compare them side by side in a simple way, mutex is like a lock with a strict owner designed for exclusive access. Semaphore is like a counter-based system designed for both access control and signaling. Mutex is simple and safe for protecting shared data. Semaphore is powerful and flexible for managing multiple resources and coordinating tasks. Now, Let's connect this with everything we have been building so far in this module. Earlier, we discussed race conditions, critical sections, and synchronization mechanisms. Mutex and Semaphore are practical tools that implement those concepts. They are not just theoretical ideas. They are used everywhere, from operating systems to multi-threaded applications. For example, inside an operating system, mutex might be used to protect access to kernel data structures, ensuring only one process modifies them at a time. Semaphores might be used to manage resource pools, like available memory buffers or I/O devices. These are real-world applications of the concepts you are learning. One common mistake beginners make is thinking mutex and binary semaphore are the same. They may look similar, but the difference in ownership and intent makes them distinct. Choosing the wrong one can lead to subtle bugs that are hard to detect. That is why understanding the difference is not just academic, it is practical. So if you remember one thing from this discussion, let it be this. Mutex is about mutual exclusion with strict ownership. Semaphore is about resource counting and signaling with more flexibility. Both are essential tools. And knowing when to use which one is what separates basic understanding from real expertise. As we move forward into problems like producer, consumer, and readers, writers, you will see these concepts come alive in even more practical scenarios. And that is where the real power of synchronization starts to show. That is it for this video. See you in the next one.